This video is going to be on Chapter 6 of the CCNA 1 course, the network layer. We just finished up Chapter 5, which was the Ethernet layer. So we're working our way up the OSI model as we go along here. Chapter 6 is the network layer, and we're going to be going over the network layer protocols, routing, routers, configuring a Cisco router in this chapter. So as we talk about network layer protocols, there's really two that are real important, which are IPv4 and IPv6. We've seen ICMP, but we don't really talk about that much in this chapter. Okay, so the network layer, of course, the network layer is only involved when you're leaving the network. In the previous chapters, we've talked about the data link layer along with Ethernet, and that was all basically as you're in your same local area network. The network layer gets involved when, well, you're leaving your network. The network layer is responsible for addressing end devices, as in giving them an IP address, taking the segment from the transport layer and adding a network layer header on it, or a packet header, IP header, onto that information. Also responsible for making routing decisions, choosing the best path along the route to get to the destination, making decisions, how that's going to work, basically fault tolerance if a device goes down, being able to route around a device. So it's making those routing decisions. Also, as it gets to the destination, you're de-encapsulating the network layer data. So that's going to happen and send up towards the transport layer only when you get to the destination device. As your data is moving through the network, you're really only de-encapsulating up to the network layer, checking the IP. Based on the IP, the router is making a decision as to where that data should go. So as we said before, there are two protocols that we discuss most in the network layer, which is IPv4 and IPv6. So that's what we'll be talking about as we go along through the chapter. Alright, characteristics of the IP protocol. And here you have the transport layer PDU as a transport layer header or segment header to the data, because you work with segments in the transport layer. Make sure that everything arrives and gets reassembled in order, and make sure that things, well, or packets, your information actually does arrive and isn't dropped during the process. So this is where you're making sure that the recipient actually received each segment or packet of the data. So by having these layers separate, the IP or the network layer can work kind of independently of the transport layers. Same thing with the data link. Doesn't matter what data is in there, the IP header can be slapped on there, whether it's IPv4, whether it's IPv6, or if any other protocol were to be developed in the future, those protocols could work independently of what's going on in the layers above. So some characteristics of IP: it's connectionless, which means no connection is established before sending data, sending your data and sending your packets. That's not something that's done by the network layer or by IP. Best effort, well, just means that it's going to make its best effort to deliver the packet successfully. Again, checking whether or not a packet got there is not the job of the IP or the network layer. There's other layers to handle that. And it's media independent. Doesn't matter what it's traveling over, fiber, wireless, whatever. Again, that's not something that IP is concerned with. So in fact, the media and dealing with that, we've already saw that's the job of layer 2 on down. So different layers take care of those items. Inherently, IP is connectionless, best effort, and media independent. Doesn't care about any of those things. It's going to make its best effort to get things delivered, doesn't establish a connection, and doesn't care what type of media you're using. So you've got the sender doesn't know if the receiver is present, if the letter arrived, if the receiver can even read the letter. The receiver doesn't know when it's coming. So as the sender, I'm not even sure if this person has moved, if they're there. If they are there, is my penmanship so bad that they can't even read the letter? And the person who is on the other end doesn't know when that letter's coming. Okay, so that's connectionless, the connectionless concept that we have there. So again, the connectionless concept on your computer's end, you know that I don't know, maybe a web server is supposed to be there. You type in www.something.com. Maybe it's down, maybe it's moved. Who knows? Okay, and the server itself, of course, doesn't know when you are going to try to access it. So that's the concept of the connectionless aspect of IP. And then we have best effort, which we kind of discussed a second ago, in that it's going to do its best to get your packet to its destination, but some packets may be lost en route. As I said before, there are other protocols at different layers to make sure that delivery happens. IP doesn't really care. It's going to, well, not that it doesn't care. It does its best, but if its best isn't good enough, then oh well. That's life. So packets may be dropped typically depending on the upper layer protocol used. If a packet's dropped, it'll get resent. In some situations, it isn't going to impact you so much if a packet's dropped and doesn't get resent. So there is a protocol in place that will not resend a lost packet, but most of the time you are going to be resent that lost packet. And media independent doesn't care whether you're sending over copper, serial, fiber optic, whatever, wireless. IP is not concerned with that. That's the job of lower layer protocols to be concerned about that. Alright, so we're going to discuss the IPv4 packet and its different sections. So with the IPv4 packet header, you're going to want to be familiar at least a bit with the sections that are highlighted here. You've got the version, which would be IP version 4, IP version 6, IP version 4 in this situation. You've got differentiated services, which has to do with quality of services. You've got the differentiated service code point, which is what DSCP stands for. ECN, explicit congestion notification, you've got there as well. So this all has to do with the quality of service, the type of service that's involved to make a quality of service decision. You probably don't need to know these two, but just know what differential services in general are. Time to live, you definitely need to know. That's how much time your packet's going to live before it just gets dropped, so it doesn't cause extra network congestion. The time to live is also referred to as a hop count. How many routers can your packet hit before it is just dropped? And maybe it's got lost in the transfer of one place to another, and it's just bouncing off routers endlessly. You don't want this packet just kind of off on the internet on a wide area network to just bouncing off routers. So if it has a time to live of 50, it'll bounce off 50 routers, then be dropped. 20, it'll bounce off 20 routers and be dropped. So that's what your time to live field is. Your protocol identifies your next level protocol. That could be something like UDP or TCP, which are both transport layer protocols. Then, of course, you got your source IP and your destination IP address. You've got a couple other things in here. The identification, flag, and fragment offset do keep track of fragments. But really, you want to know the ones that are highlighted here. So make sure you keep track of those and know those. All right. We've got the IPv6 packet. Apparently we have IP depletion going on. There's only 4 million IPv4 addresses. What are we going to do? We're going to go to IPv6 supposedly at some time. I always keep hearing a couple years from now, and I heard that a couple years ago and a couple years ago. So will we ever really transfer over? Apparently we're supposed to have to, but it seems like we're quite resistant to it. Because IPv6 addressing really doesn't seem the friendliest to most people. Well, it's not that bad. But anyhow, we had 4 billion IPv4 addresses, and with IPv, which is a 32-bit address, IPv6 is a 128-bit address, and you've got, well, 340 undecillion, which I believe is 21 zeros. I'll let you count those zeros. I'm not going to. And they equate that to, it's the same amount. If you took each grain of sand on the planet, counted it, that's pretty much what you'd come up with. So bottom line, we're not going to run out of IPv6 addresses unless we go to those other 7 planets that were discovered and populate them. Actually, before we take a look at this, let's go back up one level again and discuss these items here. So with IPv6, we just talked about the increased address space, improved packet handling. The IPv6 header is more simplified than the IPv4 header, so that's going to improve your packet handling. It eliminates the need for network address translation, because with IPv4 you've got private addresses and public addresses. You will no longer have those private addresses and public addresses with IPv6. IPv6, everyone will just have a unique address. Every device will have a unique address because we aren't concerned with running out of them. So those are those 3 items there. We'll move on down. So here's our IPv4 header again. You can see it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different fields. I think I counted that up correctly. It's going to be a lot more simplified in IPv6. Going down, you got 1, 2, 3, 4, 5, 6, 7, 8 different fields. So simplified, easier to read. It's just that the different sections mean something different than they did in IPv4. In fact, they are labeled differently in some situations. So we still have the same version field here. I didn't say before, but the version for IPv4 would be 0100. The version for IPv6 is going to be 0110. Also have our traffic class, which is the equivalent of the differentiated services field in IPv4. The flow label field is a field that's 20 bits in size. It suggests that all packets with the same flow label get the same type of handling by routers in the routing process. You've got the payload length, which is the length of the data portion of the IPv6 payload. You've got the next header, which is the equivalent of the protocol field from IPv4. It lets you know which upper layer protocols are being used. Hop limit, which is the equivalent of time to live. Hop limit, and time to live, basically the same thing. Then you got your source IP and your destination IP there, which are going to be the same as IPv4. So you can see new field, name and position change. So we talked about those and how they have equivalents in the IPv4 as well. So that is the IPv6 header, a little bit more simplified. So you've got better routing efficiency for performance and forwarding rate scalability as an advantage for IPv6. No requirement for processing checksums. Simplified and more efficient extension header mechanisms as opposed to the IPv4 options field. And flow level field for per flow processing. No need to open the transport inner packet to identify the various flows of traffic. So you've got those as your advantages for IPv6. Who knows, that may be a test question asking you, what are the advantages of IPv6? Check 2 of the 5, or check as many of these 5 as apply. So, could be a test question. Alright, we just talked about this. Oh, I guess I could have waited to just read it off, but there it is. Same thing I just said on the previous slide. Version traffic class equals priority, or is the equivalent of the differential services field of the IPv4. You got the flow label. Everything with the same flow label will receive the same handling. Yada yada yada. So we already talked about that. And we've got routing coming up next. Explaining how a host uses the routing tables to direct packets to itself, a local destination, or default gateway. Compare host routing table to a routing table in a router. So here we go. Alright. So we have three types of destinations. You could either be, well, talking to yourself, which makes your computer a little bit crazy in some people's minds. You could be talking to a local host, so you could go from one device to another, okay, on the same network. Or you could be talking to a remote host on a network that could be a hop away, quite a few hops away. Who knows? So we're going to talk about the different types of forwarding decisions. Okay. Default gateway is, well, your router, your portal off of your network is your default gateway. So that's always going to be the IP address of the router on your network. It has a local IP address within the same range as the other hosts on your network, and it can take the data and forward it out. Therefore, your gateway is the gatekeeper. You need to use it to get off the network. Okay, so the interface on your router is the default gateway off the network. Okay, so it's usually going to be, what is going to be, always in the same local network here. A router might have a few networks attached to it. So this network for this interface over here is going to have a certain IP address. The interface here that's connecting to remote networks is going to have a different IP address over on the right side here. So to bring up your routing table on your PC, you have the command netstat-r, which brings up your routing table. You can see the IPv4 route table down here. It includes any direct connections to your PC on the local network, your local default routes, as well as you got your default gateway in there to get to any unknown IP addresses that aren't on the network. So that 000 basically means that, well, anything else could go to the default gateway. So you've got a network destination, your subnet mask, gateway to get to said network destination, the interface that goes out, so, and the metric over on the right. Alright, router routing tables, which is what we're more concerned with here. Alright, so with your routers, you will have entries in the route table that are directly connected to your router. You'll also have networks in the routing table that are dynamically learned. So you've got, for R1, you've got a few directly connected networks, the 11.0 network, the 10.0 network, and the 200.224 network over here that are directly connected to your router. How that's going to show up in your routing table, well, you have it down here. So anything that is directly, I shouldn't say directly connected, because then you want to associate the D with directly. D, think more of as dynamic. Okay, it's a dynamic connection. It's learned through some routing protocol. The D actually means EIGRP routing table, or eGRIP, however you want to pronounce it. So those were dynamically learned. We'll talk about that, I guess, in just a second. But your directly connected ones are going to have the C and the L. The C basically stands for what network you're directly connected to. The L stands for the link or the interface that you're connected through. Okay, so for instance, you have the C here for 192.168.10.0. That's this network up here. Okay, how are you connected to that network? Through this interface, okay, or that link, the 10 192.168.10.1 interface. That's how you're connected to the 0 network. So for any directly connected network, you are going to have two entries. The C means basically directly connected, and the L is the local address on that interface connecting you to the network. You can also see out here, pretty important, is which interface is it, the Gigabit Ethernet 00. In this case, down below we have Gigabit Ethernet 01, Gigabit serial 0000. Okay, it's going to be important for testing purposes that you know this stuff. You're going to be asked which interface is connected to such and such network, and you're going to have to know the answer to that. Also, for the dynamically learned networks, you have a little bit of a different situation. So for this EIGRP entry, for instance, how do you know about this 10.1.1.0 network? It's not directly connected to you. It's actually over here. Your router is going to say, well, I learned that from this router here through 209.165.200.226, which just happens to be the interface of this router over here that's connected to, or shared the information with, I should say, R1. Okay, so it's going to tell you the network that was learned dynamically and which device or interface shared that information with your router. Okay, so network here, how it learned it there. All right, same interface shared, or same device shared, the information about 10.1.2.0 with your router. Okay, so it learned 10.1.2.0, which is the network over here, from R2, which is 209.165.200.226.226. Okay, again, this number comes from 209.165.200, 209.165.200. The actual host address of this R2 interface is 226. That's where you get the 226 from. Okay, so that's where that information comes from. That's how you're going to read a routing table in general. The different fields specifically we have on this side. No, not quite this slide. Coming up in a second. We do have some general fields here, which is just the route source, the destination network, the outgoing interface that you see here. So go ahead and read those. Think you've had enough time. Okay, we move on. Here's the better breakdown to identifying each field and what it means. Yeah, it's going to be important to know each field here. So let's go one by one. Let's go with this first field here. Okay, that identifies the route source. We talked about how it could be D for dynamic or EIGRP. You can think of it as dynamic, I guess, but it does mean EIGRP, which is Enhanced Interior Gateway Routing Protocol. It's proprietary to Cisco. Only Cisco devices use it. You could have a D there. You could have a O, which means Open Shortest Path First. That is a universal protocol that is used. So any device could use OSPF, and in fact, it is the more common of the protocols that is used, of EIGRP versus OSPF. You got an S for a static route, which would be a route that you enter yourself. And you have a C for directly connected, as we saw before. So those are some things that could show up there in that first field that we have here. Okay, one second. All right, so the next field is going to be your destination network. That's pretty self-explanatory. That's all it is the destination network. Your next field is the administrative distance or trustworthiness of your route source. Basically, this field, the lower the better. The lower it is, the more trustworthy it is. And there's certain numbers that are associated with certain protocols. This one just happens to be a 90, which is for EIGRP. In general, well, if something's directly connected, then that's the most trustworthy. If you enter in a static route yourself, the device is going to trust that your static route is better than any dynamically learned route, so it's going to have a lower number than this. I believe a 1. So we'll talk about those numbers later on in a different chapter. Okay, the metric identifies the value assigned to reach the remote network. And again, lower numbers here are going to be preferred routes. So that's the metric it takes to reach a network. And then again, just like this guy, lower is better. Okay. We talked about this via. That's going to be, well, the router that you learned the network from, and the next hop basically along the path of your network. So in order to get to the 10.1.1.0 network here, I have to go through this interface here, the 226 interface. So that's your next hop, also the router you learned about this network from. And then you have your interface out here at the end. Okay, so the highlighted ones are really the ones you're going to pay attention to. You've got the amount of time elapsed since the network was discovered, and just the via field there, which is just how you learned it. So there is that. Taking a look at another route table. Whoops, there. Okay, so next hop address again is just the next hop along your path. Okay, so if we're in this R1 router, our next hop to get to the 10.1.1.0 network is R2 or 209.265.200.226 is what we got there. And then we'll be starting with routers. This is going to be part 2 of the video. I just split it a little bit. Should all still be in the same YouTube thread. But listening to the first part of the video, there's a lot of going on. I guess there's probably a lot of going on in all my videos. So I'm going to try to limit it. Not sure if it's going to work out all that correctly, but we'll see what happens. Go on forward. Maybe there'll just be a lot of dead air when I would be saying in the first place. So here we go. Anatomy of a router. There it is. Does not count as routers require CPUs or central processing units. You've got operating systems and Cisco devices. You got the iOS, the Internetwork operating system that Cisco devices will all have. You've got memory consisting of RAM, ROM, NVRAM, and flash. We need to know what is stored in all of those memory types inside of your router. It just so happens that that is on the next page of the presentation. So we've got in RAM, your routing table, your ARP table, your running config, all in RAM. You're also your packet buffer. In your NVRAM, you've got that startup configuration. When we issue that command, copy running config dash starting config, that's what's happening. It's going from RAM to NVRAM because, of course, RAM is volatile. And when you power down your device, all of that information RAM is forgotten. In your flash, you've got your iOS files, basically your operating system. In your ROM, you've got your post-check and limited firmware just in case your operating system were to become corrupted or missing in flash. You've got some measures you can take with that limited firmware to get your device up and running again. So it is going to be quite important to know where everything is stored there. So know this graphic a little bit. You'll probably get a question or two on that on the test. I don't know. Just a suggestion. Moving on to inside of the router. Well, there's our SDRAM inside the router. Fascinating. What's more fascinating than that? Well, we have a power supply. We have a fan down here. Yes, to cool things down, we do need a fan. Your NVRAM is right there. Your central processing unit is there as well. I think, let's see which one. Yes, this is your central processing unit. This is your advanced integration module option. It offloads processor-intensive functions such as encryption from the main CPU. That's what you have down here. So that CPU and the advanced integration module is what you have there on the slide. Moving right along as we go. We've talked about most of these ports on your router. What we haven't talked about are these WIC slots. You've got WIC slots, so you could add serial support, DSL support to your router. They're modular. There's cards you could slide in there to add support for different connection types. You also have at the bottom there your flash card slots to expand memory of the router if you were to need to. So those are the only extra items that we have there that we haven't seen on here. We've seen the USB ports, we've seen the console ports and all that good stuff. So nothing else really new there. We'll move forward. Okay, so if you were to insert a WIC slot, you could add your serial interfaces like that. That's one example of a WIC slot that could be added. The router boot up process. On this slide we have the general boot process. First thing that's going to happen is from flash your operating system is going to be loaded into RAM. Then second, your startup config is going to be loaded into the running config at a very basic level. It's broken down a little bit more on the next slide that we have here. So the first thing we have going on from ROM when you first boot up is a power on self-test, just like your computer would perform, making sure your hardware is functioning and ready to go. You got your Bootstrap program that is basically, its job is to locate the Cisco IOS and load it into RAM, whether that iOS is on the flash, TFTP server. Typically you use the TFTP server to upgrade your Cisco IOS. Your configuration file is going to be loaded from NVRAM, and then you're going to be ready to enter setup mode. So that's the whole process: power on self-test, Bootstrap, loading your operating system, loading the configuration file, and you're ready to go. At the screen that looks, well, not quite like that. That's a show version screen, but your screen with the greater than sign for user mode is what you would get to. Your show version screen is just going to show you the specifics of your version of Cisco IOS and your flash file and all other sorts of information that you have here. So you can see the software that you're running in the version there. Your Bootstrap version, what the system image file is. Okay. Let's see, I think we got more output down below. We can see how many interfaces we've got. We've got how much non-volatile memory we've got. Compact flash memory installed. So show version is going to show you all of that information. It's just a command you can issue. If you can see there, you're in privileged exec mode to make that happen. So that's where you'll find that. How are we doing on the count? All right, hopefully we are at this point forward. Configure a Cisco router. So we're going to have some commands. That was a not a We're going to have some commands to enter in as we configure our router, just like we did with our switch. Here we have the switch configuration that we've already done in class. So adding a host name, going in the console line and adding a password, your V2I lines or your virtual lines. You've got your enable secret that we did, encrypting the passwords, banner message of the day. This is basic switch configuration steps. You should know these. Hopefully you do. We'll be using them again and again, lab after lab. So if you don't know them now, you will know them soon. All right, basic router. We've got the same thing, same commands. Will typically go from router to switch in terms of basic configuration. There are some specific things, of course, that you do on a router versus what you would do on a switch. And we'll see a couple of those as we go through here. But enable secret, password encryption, banner message of the day, all that stuff, same as a switch. Okay, so you won't see anything different there. All right, so configuring interfaces was something we didn't do too much on the switch yet. We will, but we're doing it here on the router. We configured interface VLAN 1 on the switch, and I think that was about all we did. We can also configure other interfaces, but that's all we've done in class so far is configure interface VLAN 1. The router, you're going to configure your interfaces definitely with an IP address, they need it to work, to function. So you're going to have to configure an IP address. You're going to have to issue the no shutdown. And if you want to add a description to an interface, you've got that description command that you see there. So these are some things you will be adding in class. So you just get in by interface, whatever interface you want to get into. Same IP address command that we use with the switch. Description we didn't use in the switch, so that's a little new. And then no shutdown, of course, to bring it up. No shutdown is the command to turn on an interface. So there's that as we go forward. So you've got a show IP route command that we saw earlier on. We saw it in the 4:40 a.m. version of the video. Showed you how to break that down. It basically shows you the different networks that are connected to your device. Also networks that you've learned from another device. So that's maybe 25 or so slides back. You got show interfaces that display statistics for all interfaces, and you got show IP interface or show IP interface brief that displays all your IPv4 statistics for all interfaces on the router. So one's for all interfaces period, one's for all IPv4 statistics for all interfaces. That's what you're looking for there. So you've got those commands, those show commands you will need to use in the lab. I think at least one this upcoming class. So you'll see that. Configure the default gateway. Alright. So if you haven't picked it up yet, the default gateway is your router. The default gateway is the way to get off your network. So you need to make sure you have that association in your head. Staying on the network, you don't need a default gateway. Okay? You got a switch. Switch is not a default gateway itself either. You need a router. A router is your default gateway, getting you off of your own network onto another. Okay? So if you need to configure a default gateway, that IP address is going to be the IP address of your router's interface here. So your default gateway for a switch, we can configure that pretty easily. Just go to your interface VLAN 1, right where we would add a IP address. Just right after you do that, you can add IP default gateway and add in whatever that default gateway is. Set that up. Okay, and that's about it. We've configured default gateways on PCs, so don't think I need to go through that. And this is the last slide on the video. So there we go.